Welcome to the Analytics Engineering Podcast, featuring conversations with practitioners inventing the future of analytics engineering.
On this episode, we hear from Kevin Hu, co-founder and CEO of Metaplane, which is a startup in the data observability space. We talk at length about what data observability means and how the field is evolving. We draw some comparisons to the more mature software engineering observability stack, but recognize the same technology cannot be bluntly applied to the data world. We go deep in the engineering space and how it will help companies solve their data quality problems.
I am always down for a conversation where we are trying to draw parallels and inspiration from software engineering. The thing that I wasn't ready for was that we were also going to do the same thing with astrophysics. So that was super fun. And I feel like the next Cosmos reboot, Neil deGrasse Tyson better watch out.
Yeah, Kevin is a walking encyclopedia of physics facts, which is a fun part of this episode too. So without further ado, let's get into it.
Kevin, thank you so much for joining us.
Such a pleasure to be here. I'm a huge fan of DBT, the community, and the podcast. So thank you for having me.
Yeah, totally. Okay, Julia and I have a lot of questions for you. And I specifically am going to want to dig in at some point in time to the research paper that you wrote about a system you designed called Sherlock. I've been reading it. I'm fascinated. I want to know everything about it. But before we get there, we were just talking. I asked you a question before we hit record. I asked you what the geekiest thing that you liked to do when you were 10 was. And you gave me an answer that I really loved. Can you share that with everybody?
When I was 10, me and my group of nerdy friends would spend all day making custom maps in Age of Mythology and in Age of Empires too. So of course there is the usual game where you can play on pre-made maps, but we would just spend hours, maybe hundreds of hours making custom maps and these little mini games that would be distributed to different people. And actually last night, shout out to Matt, my oldest childhood friend, we were doing the same thing for Age of Empires 4 maps. So it's nice to have old friends that you can do the same things with.
I promised Julie that I wouldn't talk about this too much because no one needs to be subjected to this, but I have a lot of fond memories when Age of Empires 2 came out originally. I was in college and, you get to college and you're excited. Back in the 90s, you would be excited that it was like really good networking at the dorms there. And so I remember playing with people in my hall on campus, and we would be across the hall from each other and yelling at each other about like coordinating tactics and everything. So anyway, I think that real-time strategy games are really good fodder for data because it like gets you to look at the world from a top-down perspective and like strategic planning and everything.
Totally agreed. Like both on the most minute level of deciding whether or not to allocate one villager to mine gold versus go on a farm to even like the bigger macro level, the military versus econ. There's a lot there.
There is. Okay, great. Okay. I'll leave that behind for the future episode of the real-time strategy podcast that we're going to launch. Talk to me about your time at MIT. It looks like you have 3 separate degrees from MIT, all one after another. If I just go by the dates that you list on your public LinkedIn profile, it seems that you finished your physics degree in 2 years. Is that true?
It's not entirely true. I went to a quote unquote early college before transferring to MIT. So I had 2 years of physics classes. Yeah.
But you got a physics undergrad degree at MIT, and then you went on. Everybody in physics uses data in some way. And I think a lot of people get involved in data analysis and programming, but not everybody goes on to get a master's with a focus in data visualization. Can you talk about that? How did that come to be?
Well, after I transferred to MIT, the first course that I took was this experimental lab course called Junior Lab. And this was notorious for being one of the hardest, like, weeder classes for physics students. Like, everyone says that they love physics until they take this class and then they transfer out. And one of the real privileges of going to a school like MIT is being able to have colleagues that are really existing on another plane, like physics Olympiad gold medalists. One of them was my lab partner at the time. And I realized in going through this course where every 2 weeks you replicate a Nobel Prize winning experiment, that everyone did the experiments in the same amount of time. But where things got difficult was analyzing the data. and presenting it, where the people who didn't know how to program, in this case Python or MATLAB, and then present it in LaTeX, had a really, really difficult time. And in parallel to that, my sister was finishing up her PhD in biology. She's a neuroscientist right now. And she was collecting data on fish behavior for 5 years. And so towards the end, she was like, Kevin, can you help me analyze this data? And I thought that was the most ridiculous thing, right? That you could spend 5 years collecting this data. You're a high-powered scientist, and you're bottlenecked by R. Come on now. And so at the time, I'm
just blown away by you must have a great relationship with your sister, because I will help my sister move, but I will not help her do data analysis on fish behavior.
Well, I mean, she does the same thing for me.
And your sister has a lot of patience to study fish behavior for 5 years, but it's another story.
Yeah, we definitely do get along. And I think, looking at people like her and, thinking honestly about myself, like I was not a 10x scientist, but I was like, but maybe I could help build some tools or methods to help other people do data analysis faster and better with less friction. And that's how I got into grad school.
I want to get to Sherlock, but before we talk about the specific piece of research, I've read a lot over the years of the kind of first-person experience that it seems like a lot of academics in ML or AI experience. It feels like a kind of a pressure cooker environment to publish. There's this conference schedule that never stops, and you've always got to get your submissions in. What was your experience like as an academic in the field? Was it fun?
There are really high highs and really low lows for me in grad school. Some of the parts that weren't fun were the more political aspects of academia and the, publish or perish kind of cadence that you describe. But at the same time, I had some of the most fun in my life collaborating and meeting awesome collaborators and working with them on really curiosity-driven projects. One of them included Sherlock, where it was a very, simple question of why is it that we upload a CSV to Tableau and we have a list of cities, their latitudes and longitudes, and Tableau thinks that those are just floats, a string and 2 floats. And the thought was, if Tableau knew the semantic type of these columns, wouldn't it be able to suggest much more powerful visualizations? So we did a little bit of a...
Well, so before you go into let me just ask the question that frames this piece of research for me. So I've been involved from the outside. I'm not an academic. I am not involved in the design of complex neural networks or anything like this. But I'm like just one step out of this part of the world. And I spend all my time with much more strongly typed data. It's in a database. It's often in a relational structure. It has a column header. Maybe it exists in someone's data dictionary. And it blows me away that we understand how to take an image and put 8 rectangles in it that box the people's faces that are in it. And that's 100% just based on pixel data. And yet we cannot do the kinds of things that you're talking about here. Take a CSV and understand what is in it. That seems like we're setting the computer up with so much information. And yet, so I don't understand. Do you think it is fundamentally a hard algorithmic problem? Or is it maybe that there's just not enough commercial incentive behind it, whereas there's a tremendous amount of commercial incentive to do image-based neural networks or things like that? What's going on there?
I think that is an excellent example where to kind of bootstrap a lot of these computer vision models, we have canonical data sets like ImageNet, but the same thing isn't true for arbitrary tabular data. So I think my first response to that conundrum is that we just don't have the training data. We don't have a very large mapping from tables to the semantic annotation of those tables. So the way we went about that is honestly scraping every single table off of the web and using the column name as the ground truth label, so to speak.
Wait, go deeper, because the column name could be anything. You have to map it better than a string of text. Did you have some gold standard? You had 100 different types of columns that you were trying to map. How did that work?
Oh, we did. Yeah, you're right. We took some public ontologies that existed online. This And these came from some old school semantic web research where they tried to create taxonomies of different locations
Right.
and
Yep.
nouns. And so we took maybe the top 100 in terms of like what existed in those ontologies and what existed in the distribution of columns that we scraped from the web. And then we used like that as the response variable, the thing to predict.
Clearly, at the end of this paper, you should have seen Tableau take all of your source code and incorporate it into its code base. And now Tableau understands when you upload lat-long city names, right?
We did do it, and the model turned out to work quite well. And like the features that we fed into the model were very, silly features, I would say, of like counting the number of periods in a cell, the average length of values in a column, the number of values in a column. But across these hundreds of different features, like our ability to predict the semantic type was quite good, like 90% plus, and outperformed humans for sure. And based on like who is downloading the open source data and continuing research on this, I think it is being incorporated into production systems.
Oh, I didn't anticipate that. That's cool. That's really cool. Most academic research doesn't end up going from conference presentation to use in practice. So that's really neat to hear.
My collaborators on this paper, Chartai and Madelon, are actually research scientists at Sigma right now, and they're carrying on a lot of this research right now.
That's super cool. Yeah, it also reminds me a lot of work happening today of how do you detect PII data. I think there's a really big business impact, and it's hard to describe because it takes so many different forms. So we're seeing some companies really focusing on how do I automate the detection of PII data in a larger data set so you can be GDPR compliant, but also it's just a huge problem that's really done quite manually today. So I think there will be lots more applications of this type of understanding the form of the data in the near future.
That is a fantastic use case, for sure.
Well, this was a good introduction to you, Kevin, and some of your work. But the most of what we're here to talk about today is more about data observability. And I want to talk about this term in particular because, I noticed in software engineering, there was this moment, I want to say it was maybe 4 years ago, where people really moved away from talking about monitoring as application performance monitoring or infrastructure monitoring. And all you could hear was observability. And it was almost this like shiny new term, a completely brand new idea on something that people had been doing for a while, but it had like a very specific definition, right? It was observability really meant 3 pillars. It was metrics, tracing, and logs. And those were the 3 components that made up observability in the software engineering world. I'm now seeing something similar happen in the data world where lots of people were talking about data quality or a variance of that word, but now we're really converging on also adopting the word data observability. So I'd love to hear from you, like, what does that mean? Is data observability just another play on data quality, or does it have like a distinct new meaning in your mind?
For me, data quality is a problem that people in the real world face, and data observability is a technology. As far as I know, people who work with data don't wake up in the morning saying, oh no, my biggest problem is data observability. If you exist out there, please send me an email. But I would love to chat. But it's a technology that can be used to address data quality issues as well as other issues, but it's not necessary to solve that problem. For me, data observability is a concept that really describes like how much visibility you have into your data systems. And one useful proxy to that visibility is to what degree can you reconstruct your data at any point in time? So to give an example, if you have like a table with some numeric distribution, if you have the mean and the standard deviation of that distribution, you can construct it to a reasonable degree. If you have a column with categorical values, you can also construct that with like the number of nulls, whether it contains PII, but never fully. The goal is just to be able to know at any point in time enough that you can solve whatever problems you have at hand. And this is where it goes into the software observability world, where metrics, traces, and logs tell you about the state of your software infrastructure at various points in time.
Got it. And so the word observability really comes from like the act of observation, right? You don't have to have source truth of what's actually happening in your code or with your data, but from all of the information that you get off of what actually happened in production in real time, you can reconstruct the root cause or figure out what actually went wrong or went right, just by observing the actual actions of the system.
You put that so well. And that, goes all the way back to the original origin of observability from control theory, where given a system and the inputs into that system, how much can I control the output? That's the controllability of a system. Observability is the inverse, right? Given my knowledge of the outputs, what do I know about the internal states? And there's such an interesting history to this term, where it goes all the way back to James Clerk Maxwell, the Scottish physicist who gave us Maxwell's equations. He was trying to figure out how the heck this device called a centrifugal governor, which is used to control the speed of steam engines, worked. Because there was no like concrete physical theory about, okay, as this engine spins faster and faster, you have these two pendulums essentially kind of suspended along the sides. And it's almost like an ice skater, right? The faster they, as the arm goes out, spins slower. As they come back in, it spins faster. So he made the first concrete theory that became control theory, and it was kind of co-opted by software observability and now data observability over 100 years later.
Julia, you weren't kidding.
Yeah.
You said Kevin knew a lot about the history of physics. He's not disappointing.
He has lots of good nuggets. And it says, I don't know if they teach that in your physics PhD, but keep them coming. So cool. So that went from like the physical world, we're talking about actual, physical engine systems, to software observability. And now we're talking about data observability. But of course, you can't apply the same terminology very bluntly. And so you wrote this really good article about the 4 pillars of data observability, which has, pretty close ties to, metrics, tracing, and logs of how we talk about it in software development. But you've introduced a 4th pillar. And so you say they're metadata, metrics, lineage, and logs. Help us understand like why these are the 4 things that make the system complete and how they all fit together in actually solving the user's problems of what actually happened.
Part of the motivation to try and derive a new set of pillars is like, while there's a lot of, ink being spilt about how us in the data world can learn best practices from the software world, there are important differences as well, right? You can't copy them one-to-one without at least thinking about it a little bit critically. And for us, we try to go back to first principles and say, if we were just trying to describe any system, how do we start? And going to another physics analogy, we said, okay, if you're trying to describe this glass of water next to me, how do we do that? Well, one, there are like intrinsic properties to the water. It's the temperature, the entropy of the water, and there are also external properties, like how much water is in here. Right? I can double the amount of water, but the temperature can stay the same. I can increase the temperature, but the volume is the same. And I think the analogy in data is, what are the internal characteristics of the data, the distribution of a column, whether or not it contains PII, and what are the external characteristics? Like, what is the schema? How fresh is the data? How many rows are in the data? And you can change the distribution and you can change these external characteristics a little bit independently. Of course, they are related, but they can change without affecting the other. That's metrics and metadata. Another angle is to think about a system in terms of its interactions, right? Internal interactions and external interactions, where within a data warehouse, for example, you have the relationship between data sets, which we like to call lineage, right? Where one datum or a set of data is produced by applying an operation to other pieces of data upstream. So that's kind of relationships between pieces of data. And you also have the external relationships. Like, what machines produce this data? Who is interacting with it, either as a data producer or as a data consumer?
Yeah. I like that. It's like the core building blocks of like, what is this thing and how does it fit together in the broader system? And I think people are starting to get smarter about making sure you can track the right metadata, track lineage. Some of these things aren't really out of the box. You don't get them for free. One of the things that's always like been curious to me is if you're a software developer and you're building new software, you don't just ship it without some kind of observability or monitoring. You don't fly blind. That's like comes hand in hand with the building process. Otherwise, you have no idea how your systems are performing with customers or in the wild. But data observability, we're behind. People don't quite think about it the same way of like, I can't give this data table and put it into a dashboard or have it feed into some other system unless I have like full visibility and can observe, as you talk about, metrics, metadata, lineage, and logs. Why is that? Are we going to get there at some point, or is there something fundamentally different about the way people think about data observability versus like shipping software?
A few things come to mind. One is that the tools that we have available to us have made it a little bit difficult to get that kind of information, which is why I love the dbt cloud and metadata APIs, because finally I have a tool that makes the lineage easy for me to parse. I just grab the JSON and all the metadata and logs is very easy for me to consume. I think if it's not easy, it's there's so many other things for data practitioners to do that it's kind of not a very high priority. I would say the biggest difference and why data observability is a problem now is because the stakes are higher. For the past few decades, the main vein of data throughout organizations was decision support. This was the big use case that Edgar Codd talked about in his seminal papers, was using data to help support decisions. Today, we refer to that as like business intelligence and dashboarding. But we also see data going to a whole bunch of different use cases nowadays, right? Whether it's being reverse ETL'd back into a go-to-market tool like Salesforce so you can start targeting leads, or to train machine learning models for analyzing and allocating ad spend.
That's like a good differentiation there, right? If there's a stopgap of the human that is the final last mile to make the decision or take action, well, okay, like probably going to have some human intuition about whether the data is right or if there needs to be like some rework done. When things start being automated or you're using data as the decision maker itself, that's when things can get dangerous if things go off the rails. Like, not to be too fear tacticy, like I love like security vendors when like their biggest selling point is like painting a really scary world out there, like you must buy because if not, all these terrible things can happen. But how bad can data be? What is the worst case that people should be thinking about and guarding against?
I think you hit the nail on the head of describing the previous world where the cost of bad data was kind of the cost of bad decisions. But the stopgap was having a human, see the data and make the decision. I'm not trying to be a fear mongerer either, but I think now we've introduced a world where there are some harder to reverse and also more uncapped risks when it comes to working with data. To go back to the two examples from before, if you're feeding data back into a customer-facing system like a CRM, if you send an email, like the wrong email to the wrong people, that could have a reputational impact. And trust me, I've seen it before, for sure, that it's kind of hard to backtrack from that the moment that it starts impacting end users. And I've also seen the machine learning models, many of our customers are e-commerce shops, and the data is being fed into ad spend models or product recommender models. And once you tie it into those systems where there's no longer necessarily a human in the loop, you can honestly lose a lot of money very quickly.
Yeah, that's when your bad data can get expensive. One of the things that really interests me is there are a lot of business context needed to recognize bad data. I've had this happen to me before where I've actually shown Tristan a piece of work and I was like, here is the data, and he can spot pretty quickly because he, for whatever reason, this is a number that he cares deeply about. And so he can spot it immediately. something's wrong here. That data is not right. Whereas like for me, when I have other data points that I can spot quickly, but for that particular data point, I didn't have the context. Data work happens to be like really mechanical, precise. We do a lot of practice to make sure that we don't introduce mistakes. But how do we get more of the like qualitative things, like the business context, to trigger the like, that number doesn't feel quite right in your observability system?
That is such a good question. And I just want to +1 you for a second there by saying that, data begins and ends outside of the analytics team, right? As much as we talk about warehouses becoming the source of truth, it's not the source of any truth, right? Your Snowflake does not actually create data. So that, I totally agree that the main expertise lies in the people who are producing and the people who are consuming the data, and that there is definitely a limit to how well a system like ours or any external system can really understand the semantics, for lack of a better word. And for observability tools, I think one of the hard challenges is being able to use human time and attention effectively. Right? I mean, those are the most important, like the most valuable resources in the world. And we will need some annotation from real humans that understand what the heck is going on. But we don't want them to constantly be looking at a tool and all the tables, which is why, for us, we try and automate as much as possible and only get human feedback on the most important or uncertain anomalies.
So you're describing like a learning system. So there's a best guess that this is maybe the data is off, but you need input, annotations to learn from humans to actually improve the machine learning models. Is that a fair description?
That's exactly it. Right. For us, it's having a human in the loop giving feedback on anomalies that we send in Slack. I think that this is, part of a more broader point that there's only so much that a system can understand about your data stack, right?
Yeah.
Like everything can be working perfectly technically, but there still could be a semantic issue. Ben Stansel wrote a great blog post recently about the semantic anomaly, precisely about this topic.
Yeah, it's like the anomalies is the hard one, right? Because often you observe true anomalies in businesses, but you can like rationalize like, oh yes, we had a big sign up in dbt Cloud because we had a big event that we were pushing. And that actually makes a whole lot of sense that on today's date, we had 3x signups. But that's the kind of context that takes a lot of other business context in order to have a system accurately portray this is bad data or this is what we should expect to see.
Totally. And in that example that you brought up, we're showing a number to Tristan. How did that happen, I guess, where presenting this number and then Tristan was like, okay, I have the context needed to figure out what exactly is happening here?
I think this is fictitious. I don't think Julia's ever presented
Okay.
literally
It's
anything.
true. I have
incorrect.
the exact example. It was seats data. Yeah, Tristan knew how seats grew across our customers super well. And he's like, this doesn't make sense. And I'm like, oh, yes, you're right. But it was actually wrong data it was too much detail. But anyways, it caused us to go a little bit deeper and we got to the right answer. But it was something that the human could spot pretty quickly if you had the right context.
Gotcha. But kind of along the way, people who are otherwise looking at the data were like, looks good to me.
Yeah, exactly. So one of the things that I've observed too, and we'll call them observability platforms, Datadog being the biggest of such platform, they end up having like lots and lots of bells and whistles. Like it's not just the 3 pillars anymore. You can do very traditional things, but you can do kind of far out things like real user monitoring, sensitive data monitoring. Is Datadog going to ever get into the data space, or is it like fundamentally totally different problem? We need our own separate tools to solve this. And what does the evolution of a tailor-made data observability platform look like? Will it also have a long list of cool things that we can now solve?
Before you actually, that's a big question. Let me present my theory of how this is going to play out. All right. And you tell me if I have any of this right, because we've thought about some adjacent parts of this problem too. So like in the data space, one of the holy grails is query log data from Snowflake or BigQuery or Redshift or whatever your platform is. And it turns out that that's a real pain in the butt to get. Just making a reliable process that gets all of those log statements. Now, and this is one of the reasons why I am like a little bit frustrated with this space in data, whereas in software, I think it does better, is that if you look at like Postgres makes it super easy to observe. And it's an open source product. They assume that you are going to own and operate this thing. And so, of course, you're going to want to observe it. Whereas when you try to get query log data from a data platform, doing it, you feel like this was maybe not the first experience that they thought about as designers of the platform. So you have to, in order to do anything useful at all, like you've been talking a lot about user experiences that you want to deliver to people, but in order to be able to deliver any user experiences at all, you have to start by like getting all of this different data from all these different places. And I think that what happened with Datadog and a couple of other tools is that they found a way to convince people at scale to put their data in the solution. And then once you've got the data there, then you can start building all these product adjacencies on top of it. But oh my gosh, it's hard to go from 0 to 1 in terms of like getting all this data in the first place. How good's my read?
Your read is spot on. That the hard part is like getting that first, connection point, and that, the example of Snowflake query logs is a great one because you know how many rows there are in that system table, right? And how long it takes to query that and to store it and to, let users arbitrarily query it. There's so much redundancy and the data is coming at such a high velocity that it is hard to parse through for sure. And this also applies to all of the other connection points that we have, even though they might be a little bit simpler versus query history. For example, hitting the Tableau API to get all of the fields and calculations, worksheets and dashboards that you might have, along with all of your dbt metadata and all of your Snowflake information schema metadata. There is a lot of upfront work, but
this is the part when you're like, and we've figured out how to do that really well. You're right. It's a lot of integration work. You referenced one of Ben Stansel's, I think it was a December post from Ben. He also wrote one recently that was, I think, focused on this like integration problem where in order to have a single picture of metadata, you almost have to like build a 5-tran Airbyte style tool just to go out and ingest all the different metadata so that you can operate on it.
I think the viability of doing that depends on how the utility of the tool scales with the amount of integrations you have. For a given customer, that seemed a little bit abstract, but in like a data analysis tool, I would say if you're missing a key integration, the rest is much less valuable. So that is important to like cover all of the bases. Whereas at least what we've seen is if you hit the big bases, like integrating with Snowflake, integrating with dbt, and integrating with Looker, which is by far the median data stack for our customers, then you've already covered a lot of the bases in terms of metadata, and the rest are like optional.
So Julia, back to your original point, how soon is Datadog just going to try to own data observability too? It seems like you're based on like the places that you have to go, the engineering problems you have to solve. My guess is that your answer is, well, it's a pretty different problem to solve.
They definitely have the name for it, for sure. They might already have the perfect name for a data observability tool, Datadog. But like you're saying, the audience is different. The types of integrations they would have to build are different. And what I'm willing to like bet on is almost a case of like analogous evolution where like right now we're building a ClickHouse integration. And the people who are asking us for a ClickHouse integration are mostly software engineers who are doing data work. They wouldn't call themselves data people or purple people, but they're essentially doing data work. And I was looking into ClickHouse and it's like, wow, this is so similar to the OLAP databases in our world, right? Snowflake, Redshift, and BigQuery. But it almost emerged in a whole different ecosystem. It's almost like porcupines and cacti both evolved spines. right? But they're not related to each other. It just turned out that having big pokey things stops you from getting eaten a lot of the time.
That's so good.
But it's like people wouldn't, I think, generally put ClickHouse and Snowflake into the same bucket in terms of technologies to evaluate. And similarly, I would imagine that Datadog builds something similar. They might not call it data observability, and it might not be, marketed or sold to data people, but that it's like functionally very similar.
Yeah, it's interesting. I'm bullish on ClickHouse as a technology. So I do think data people will start adopting it more, especially when they get a cloud-hosted version of ClickHouse that's really seamless. Do you think the worlds will converge? But for me, there's like a fundamentally different thing about data, which is it has so much gravity and it has history, and that makes it unique and challenging to work with, and for lots of different reasons. Like in the trend in software development is like you spin up a container and you spin it down and you have your entire system up, and then you trash it and like you rebuild it again in seconds, and you're just like constantly starting over from scratch. Whereas in data, like if I dropped all your data, we have a huge problem. And so that fundamentally, like you have to keep track of this thing that will never go away and how it evolves and what shape it takes and all the dependencies, and it has just a memory to it that software doesn't.
Totally. Yeah, like people would say that treat your infrastructure like cattle, right? You kind of swap out one container for the next. We can't do that in the data world. Our data is not only not like cattle, they're like thoroughbreds, right? Where the lineage matters, right? And it's very precious. Even the smallest piece of data.
Did you come up with that on the spot?
Yeah.
Wow. Wow. Thoroughbreds and lineage. That's great.
But we can, but it's true. Like you can't just get your Fivetran connector back up and call it a day, right? You have to backfill everything, right? And every second that passes, right, you're missing more and more data, and the stakes get higher and higher.
Here's a question a little bit out of left field, but it's something that I have been pondering recently. DBT kind of, in this like kind of idempotent programming model, we take some shortcuts. We don't actually have to deal with schema migrations because we're like, look, we're just the transformations that things pass through. If you have a new schema at the beginning and you need a new schema at the end, then destroy the whole thing and rebuild it. Or, you can do some slightly more clever things, but a lot of times we don't have to worry about schema migration. But observability, you're really treating metadata as the first-class citizen. And if that schema changed, you have to understand that this field that used to be called this is now called this in order to be able to maintain that. Have you thought deep? I know that you're still in early days, but is this a problem that you've thought much about yet?
I think after detecting freshness issues and row count anomalies, being able to track schema changes is probably the biggest problem for our customers. And to do it in a, not just like the level one way of like, these were the columns that were dropped and these were the columns that were added, although that is very helpful, but being able to dig in a little bit deeper into the, like detecting the types, right? Like given a transactional database, Postgres, being replicated into Snowflake, how can I automatically infer which source tables lead to which target tables without having a human go through and have to annotate all of that? This is something that we're actually working on right now. Going back to the point of human time is so precious, right? We don't want people to have to do the rote work.
So are you able, I'm curious, like you talked about the most common stack you have is often Snowflake, dbt plus Looker. Is everything out of the box? Can you give people lots of interesting insights just by connecting to those three systems? Or do you have to, as a user of Metaplane, like do a lot of implementation to define your metrics or help give Metaplane the raw source information that it then can tell you insights off of?
Our typical customer implements Metaplane in less than like 15 minutes, plugging in your Snowflake credentials, your dbt API key, your Looker site and API keys, and we'll give you some useful things like tracking schema changes and tracking job runs. And we'll also blanket a lot of your warehouse and tests on freshness and row counts after a training period, because we have to collect enough historical data to start. But that's kind of like out of the box for our users. And to go one level deeper, you can apply more detailed tests, like tracking the uniqueness or the distribution of a field. or creating custom SQL. But the idea is that we want to make observability as easy as possible, right? Like data people are so busy, and data observability is not the biggest problem that most teams are facing. So we want to make it kind of like an afternoon project instead of a quarterly objective to bring it on.
Yeah, that makes a lot of sense. Make it turnkey. So we asked this question to all our guests to wrap up, and you can talk about data observability or pick something completely out of left field. But what do you hope will be true of the data industry looking 10 years out?
No matter what vendors like me will say, I think the number one problem facing most data teams today is hiring, trying to bring on the right people for the job and help grow the data team. And I think things are trending in the right direction, but that there's still so much work that we can do to make sure that people talk about software being this enormous industry and data will become an equally enormous industry. But to boil that down, like down, what it comes down to is like one single person making the decision to take their career into the data world versus some other industry. And like we know, be on the opposite side, that working in data can be very engaging and very fun, and you get to learn a whole bunch of different things and talk to interesting people. But my hope is that we can make it as easy as possible for that person making the decision to say, okay, maybe I'll take my career in the direction of data. And there's so much that we can do to do that, right? For society to invest in its citizens, for companies to invest in its more junior employees, for people to invest in themselves, making that super easy. My hope is that in 10 years, like there's almost no barrier to working in data if you want to.
What a great answer. I want that too. So often we get, and I do this too. I think that on the episode when I was in the hot seat, my own answer had to do with like a lot of the problems that I am working on solving every day. But I think that you are absolutely correct that there's an order of magnitude, at least, if not more, humans that we need to be solving these problems alongside of us. Kevin, where can people find you if they want to engage more deeply with you or with Metaplane?
Well, like you said before the show, there's a whole lot of Kevin Who's out there. So if you search for there's a lot of us. And yes, we do have a Facebook group. But if you want to learn more about Metaplane, go to metaplane.dev and follow Metaplane on Twitter. And I'm Kevin ZENGHU Zhenghu on basically every platform. Would love to get in touch, or also hit me up on the DBT or Locally Optimistic Slacks.
Amazing. Thanks so much for hanging out today.
It's a lot of fun.
Totally my pleasure. Thank you.
The Analytics Engineering Podcast is sponsored by DBT Labs and is hosted by Tristan Handy and myself, Julia Schottenstein. Have comments, questions, or guest suggestions? Email us at podcast@dbtlabs.com. Our producers are Jeff Fox and David Krevitt. If you enjoy the show, please drop a review or share it with a friend. Thanks for listening.